Picture this: a single burst of energy, brighter than 1 billion suns, flashes across the universe in just a few seconds. What could possibly create such an unimaginable explosion? This is just one of the countless mysteries lurking in the vast expanse of space, where the rules of physics, as we know them, are constantly challenged. Today, we're diving into the unknown, exploring 25 of the most baffling and awe-inspiring phenomena that have left scientists scratching their heads for decades. From the mind-bending power of gamma-ray bursts to the eerie whispers of dark matter, the universe is full of secrets waiting to be uncovered. So, buckle up and prepare to journey into the cosmos, where every discovery raises more questions than answers. By the end of this video, you'll not only learn about these cosmic enigmas, but also gain a deeper appreciation for just how much we still have to explore. Ready to unravel the mysteries of the universe? Let's begin. Now, let's zoom in on one of the most explosive and enigmatic events in the cosmos: gamma-ray bursts. Imagine for a moment a flash of light so powerful that it outshines entire galaxies, releasing more energy in a few seconds than our sun will emit in its entire lifetime. These are gamma-ray bursts, and they are among the most energetic phenomena ever observed in the universe. First detected in the late 1960s by military satellites designed to monitor nuclear explosions, these bursts were initially a complete mystery. Scientists were baffled by their sudden appearance and incredible intensity. What could possibly produce such a colossal release of energy? Gamma-ray bursts are essentially brief but incredibly intense flashes of gamma rays, the most energetic form of light. They can last anywhere from a fraction of a second to several minutes, and they originate from distant galaxies billions of light years away. Despite decades of research, their exact origins remain one of the greatest puzzles in astrophysics. Some theories suggest they are caused by the collapse of massive stars into black holes, while others propose they result from the collision of neutron stars. Yet, even with these ideas, the sheer power and unpredictability of gamma-ray bursts continue to challenge our understanding of the universe. What makes them even more intriguing is their rarity. While they occur somewhere in the universe almost daily, detecting them requires precise timing and advanced technology. And even when we do catch one, the fleeting nature of these bursts leaves scientists with more questions than answers. Why do they vary so much in duration and intensity? What exactly triggers them? And could they pose a threat to life on Earth if one were to occur nearby? These are just some of the mysteries that make gamma-ray bursts a fascinating and enduring topic of study. As we continue to explore the cosmos, gamma-ray bursts remind us just how much we still have to learn about the universe. They are a testament to the raw, untamed power of space, and a reminder that even the most advanced science can only scratch the surface of its secrets. So, as we move forward, keep this in mind: the universe is full of surprises, and gamma-ray bursts are just the beginning. Now, let's take a closer look at what might be behind these astonishing cosmic explosions. One of the leading theories about the origins of gamma-ray bursts involves the collapse of massive stars. Picture a star many times larger than our sun, reaching the end of its life. As it exhausts its nuclear fuel, its core collapses under its own gravity, forming a black hole. In the process, jets of energy are launched outward at nearly the speed of light, producing the intense gamma-ray burst we observe. These events, known as hypernova, are thought to be responsible for the longer bursts, lasting several seconds or even minutes. But even with this explanation, the sheer scale of energy released remains hard to fully comprehend. Another compelling theory points to the collision of neutron stars. Neutron stars are the incredibly dense remnants of supernova explosions, packing the mass of a star into a sphere just a few miles across. When two of these ultra-dense objects spiral into each other, the resulting collision can unleash a tremendous burst of gamma rays. This scenario is believed to produce the shorter bursts lasting less than 2 seconds. Yet, while these collisions are incredibly violent, they still don't fully account for the extreme variability in the bursts we observe. Why do some last mere milliseconds while others stretch on for minutes? And why do their energy outputs vary so dramatically? Adding to the mystery, some gamma-ray bursts seem to defy these explanations altogether. For instance, certain bursts exhibit patterns or features that don't neatly fit into either the collapsing star or neutron star collision models. This has led scientists to explore other possibilities, such as the involvement of magnetars neutron stars with incredibly strong magnetic fields, or even more exotic phenomena like primordial black holes. But so far, none of these ideas have provided a complete answer. What's truly fascinating is how much these bursts challenge our understanding of physics. The energy involved is so immense that it pushes the limits of what we know about matter, gravity, and the behavior of the universe itself. And while we've made significant strides in detecting and studying gamma-ray bursts, their fleeting nature and immense distance make them incredibly difficult to study in detail. Each burst we observe raises new questions, leaving scientists with a tantalizing puzzle that continues to inspire both curiosity and awe. As we piece together the clues, one thing is clear: gamma-ray bursts are more than just cosmic fireworks. They are windows into some of the most extreme conditions in the universe, offering glimpses of processes that we can barely imagine. And as we continue to explore, they remind us that the universe is far stranger and more dynamic than we ever thought possible. So, as we move forward, let's keep our eyes on the skies, because the next burst could hold the key to unlocking even greater mysteries. Now, shifting our gaze to another cosmic enigma, let's dive into the mystery of fast radio bursts. Imagine a flash of radio waves brighter than 1 billion suns, appearing out of nowhere and vanishing in less than the blink of an eye. These are fast radio bursts, or FRB, and they're one of the most puzzling phenomena in the universe. First detected in 2007, these bursts last only a few milliseconds, yet they release as much energy as the Sun does in 80 years. What makes them even more intriguing is their unpredictability. Some occur just once, while others repeat at irregular intervals, adding layers of complexity to their study. The suddenness of these bursts makes them incredibly difficult to catch. By the time astronomers detect one, it's already gone, leaving behind only a faint trace of its existence. This fleeting nature has made it challenging to pinpoint their origins. Are they coming from within our galaxy, or are they signals from the far reaches of the cosmos? The truth is, we still don't know. What we do know is that they travel vast distances, often billions of light years, before reaching us. This means they carry information about the universe's structure, passing through galaxies, gas, and dust along the way. Yet, their exact source remains shrouded in mystery. Adding to the intrigue, some fast radio bursts have been traced back to specific regions of space, but even then, their origins are unclear. Could they be the result of cataclysmic events, like the collision of neutron stars or the collapse of massive stars? Or are they linked to more exotic objects, such as magnetars neutron stars with incredibly powerful magnetic fields? Some scientists have even speculated about the possibility of artificial origins, though this remains a fringe idea. The truth is, every burst we detect raises more questions than answers, keeping astronomers on their toes. What's truly remarkable about fast radio bursts is how they challenge our understanding of the universe. They're like cosmic whispers, carrying secrets from the farthest corners of space. And while we've made progress in detecting and studying them, their brief and unpredictable nature means we're still only scratching the surface. Each burst is a clue, a piece of a puzzle that could reshape our understanding of the cosmos. So, as we continue to explore, let's keep our ears tuned to the universe, because the next burst might just hold the key to unlocking one of its greatest mysteries. Now, as we venture deeper into the mystery of fast radio bursts, let's explore the leading theories that attempt to explain these fleeting cosmic signals. One of the most widely accepted ideas points to neutron stars, the dense remnants of massive stars that have exploded in supernova. These incredibly dense objects, often no larger than a city, can spin rapidly and generate intense magnetic fields. Some scientists believe that fast radio bursts could be caused by magnetars, a type of neutron star with magnetic fields trillions of times stronger than Earth's. When these magnetars experience starquakes or magnetic flares, they might release bursts of energy that we detect as fast radio bursts. Yet, while this theory fits some observations, it doesn't explain all the bursts we've detected, leaving room for other possibilities. Another compelling theory involves black holes, the enigmatic giants of the cosmos. When black holes consume matter, they can produce powerful jets of energy that shoot out into space. These jets, traveling at nearly the speed of light, might generate the intense radio waves we observe as fast radio bursts. Alternatively, the collision of two black holes or a black hole and a neutron star could release a massive burst of energy, creating a signal that travels across the universe. However, these events are rare, and not all fast radio bursts match the expected patterns of such collisions, keeping this theory in the realm of speculation. Then there's the more controversial idea: could fast radio bursts be artificial in origin? Some researchers have suggested that these bursts might be signals from advanced extraterrestrial civilizations. The idea is that an intelligent species could use powerful beams of energy to communicate across vast distances or even propel spacecraft. While this theory captures the imagination, it lacks concrete evidence and remains on the fringes of scientific discussion. Still, the possibility, however slim, reminds us of how much we have yet to learn about the universe. What makes fast radio bursts so fascinating is that no single theory can fully explain them. Each burst we detect seems to add another layer of complexity. For example, some bursts repeat at irregular intervals while others occur just once. This inconsistency makes it difficult to pin down a universal explanation. Are we dealing with multiple sources, each producing bursts in different ways, or is there a single, yet-to-be-discovered phenomenon behind them all? The truth is, fast radio bursts are a cosmic puzzle that continues to challenge even the brightest minds in astronomy. As we piece together the clues, one thing is clear: fast radio bursts are more than just fleeting flashes of energy. They're windows into the most extreme environments in the universe, offering glimpses of phenomena we're only beginning to understand. Whether they're born from the violent deaths of stars, the collisions of black holes, or something entirely unexpected, each burst brings us closer to unraveling the mysteries of the cosmos. And as we continue to listen to the whispers of the universe, who knows what secrets the next burst might reveal? Now, shifting our gaze to another cosmic enigma, let's delve into the shadowy realm of dark matter. Unlike the stars, planets, and galaxies we can see, dark matter is invisible. It doesn't emit, absorb, or reflect light. Yet, despite its elusive nature, dark matter plays a crucial role in holding the universe together. Scientists estimate that dark matter makes up about 27% of the universe's total mass and energy, far outweighing the ordinary matter we're familiar with. But if we can't see it, how do we know it's there? The answer lies in its gravitational effects. Dark matter's presence is inferred by the way it influences the motion of stars and galaxies. For example, when astronomers observe galaxies spinning, they notice that the outer regions rotate much faster than they should based on the visible matter alone. This discrepancy suggests that there's an unseen mass dark matter, exerting a gravitational pull, keeping these galaxies from flying apart. Similarly, the bending of light from distant objects, a phenomenon known as gravitational lensing, reveals the presence of massive, invisible structures in space. These observations point to dark matter as the hidden scaffolding of the cosmos, shaping the large-scale structure of the universe. But what exactly is dark matter? That's the million-dollar question. Despite decades of research, its true nature remains one of the greatest mysteries in science. It doesn't interact with electromagnetic forces, meaning it doesn't produce or block light, making it incredibly difficult to detect directly. Scientists have proposed various candidates, from weakly interacting massive particles, or WIMP, to actions, hypothetical particles that could explain dark matter's properties. Yet none of these have been conclusively observed, leaving us with more questions than answers. What makes dark matter so fascinating is that it challenges our understanding of physics itself. The standard model of particle physics, which describes the fundamental particles and forces, doesn't account for dark matter. This means that uncovering its secrets could revolutionize our knowledge of the universe, potentially revealing new particles or even entirely new laws of physics. As we continue to search for answers, dark matter stands as a reminder of how much we still have to learn about the cosmos. It's a hidden force silently shaping the universe, and its discovery could unlock some of the deepest mysteries of existence. Now, let's turn our attention to the ongoing quest to uncover the secrets of dark matter. Despite its invisible nature, scientists have been tirelessly working to detect and understand this mysterious substance. One of the most ambitious efforts is the use of underground detectors, like the Large Underground Xenon Experiment, or LUX. These experiments are designed to catch rare interactions between dark matter particles and ordinary matter. Shielded deep underground to avoid interference from cosmic rays, these detectors wait for the faintest signals that could hint at dark matter's presence. So far, the results have been elusive, but each experiment brings us closer to narrowing down the possibilities. Another approach involves particle colliders, such as the Large Hadron Collider. By smashing particles together at incredibly high speeds, scientists hope to create dark matter particles in controlled conditions. While the collider has successfully discovered other particles, like the Higgs boson, dark matter remains out of reach. This doesn't mean the efforts are in vain. Every experiment that doesn't find dark matter helps refine our theories and guides future research. Astronomers are also using the cosmos itself as a laboratory. By studying the distribution of galaxies and the way light bends around massive objects, they can map the presence of dark matter on a grand scale. Projects like the Dark Energy Survey and the upcoming Vera-C Rubin Observatory aim to create detailed maps of dark matter's influence across the universe. These observations provide critical clues about where and how dark matter might be hiding. Yet, despite these cutting-edge efforts, dark matter continues to evade detection. Its elusive nature challenges not only our technology but also our understanding of physics. The fact that dark matter doesn't interact with light or ordinary matter in ways we can easily observe makes it one of the most stubborn puzzles in science. This ongoing search is a testament to human curiosity and determination as we push the boundaries of what we know in pursuit of answers. What makes this search so compelling is the potential for discovery. Unraveling the mystery of dark matter could fundamentally change our understanding of the universe. It might reveal new particles, forces, or even dimensions that we've never imagined. For now, dark matter remains a shadowy enigma, but every experiment, every observation, and every theory brings us one step closer to shedding light on this cosmic mystery. The search continues, and with it, the promise of unlocking one of the universe's greatest secrets. Now, shifting our gaze to another cosmic enigma, let's explore the mysterious force known as dark energy. Unlike dark matter, which pulls galaxies together, dark energy is believed to be responsible for the accelerating expansion of the universe. This discovery, made in the late 1990s, completely reshaped our understanding of the cosmos. Scientists observed that distant galaxies were moving away from us faster than expected, suggesting that something was pushing the universe apart at an ever-increasing rate. That something is what we now call dark energy. What makes dark energy so baffling is that it makes up about 68% of the universe's total energy content, yet we know almost nothing about it. It's not a particle like dark matter, nor does it interact with light or matter in any way we can detect. Instead, it seems to be a property of space itself, a kind of energy inherent to the vacuum of the universe. This idea is tied to Einstein's concept of the cosmological constant, which he initially introduced and later dismissed as a way to explain a static universe. Ironically, it might now hold the key to understanding why the universe is expanding faster and faster. One of the leading theories suggests that dark energy is a constant force, evenly distributed throughout space. If this is true, it means that as the universe expands, more space is created, and with it more dark energy. This would explain why the expansion is accelerating. However, other theories propose that dark energy might change over time or vary in strength across different regions of the universe. These ideas are still being tested, but so far, no definitive answers have emerged. The challenge in studying dark energy lies in its subtle effects. Unlike dark matter, which we can indirectly observe through its gravitational influence, dark energy's impact is only noticeable on the largest scales across billions of light years. To study it, scientists rely on tools like supernova, which serve as cosmic mile markers, and large-scale surveys that map the distribution of galaxies. Projects like the Dark Energy Survey and the upcoming Euclid Space Telescope are designed to gather more precise data, hoping to shed light on this elusive force. Despite these efforts, dark energy remains one of the greatest mysteries in modern science. Its existence challenges our understanding of fundamental physics, forcing us to reconsider what we know about gravity, space, and time. Unlocking the secrets of dark energy could revolutionize our understanding of the universe, revealing new laws of physics or even entirely new dimensions. For now, it stands as a reminder of how much we still have to learn about the cosmos. As we continue to probe its mysteries, one thing is certain: the universe is far stranger and more complex than we ever imagined. Now let's dive deeper into the profound implications of dark energy and how it challenges the very foundations of physics and cosmology. Dark energy isn't just a mysterious force, it's a puzzle that forces scientists to rethink some of the most fundamental principles of the universe. For centuries, we've relied on theories like Einstein's general relativity to explain how gravity shapes the cosmos. But dark energy throws a wrench into this framework, suggesting that there's more to the story than we ever imagined. One of the biggest challenges dark energy presents is its effect on the universe's expansion. According to general relativity, gravity should slow down the expansion of the universe over time. But dark energy seems to do the opposite, accelerating the expansion instead. This contradiction has led scientists to question whether Einstein's theory is incomplete or if there's an entirely new force at play. Some researchers are even exploring the possibility that our understanding of gravity itself might need to be revised, opening the door to entirely new physics. Another intriguing aspect of dark energy is its connection to the concept of the vacuum of space. In quantum physics, empty space isn't truly empty, it's teeming with virtual particles that pop in and out of existence. These particles are thought to contribute to a form of energy known as vacuum energy, which some believe could be the source of dark energy. However, when scientists calculate the expected amount of vacuum energy, the numbers don't match what we observe in the universe. This discrepancy, known as the cosmological constant problem, is one of the biggest unsolved mysteries in physics. Dark energy also raises questions about the ultimate fate of the universe. If the acceleration continues, galaxies will eventually move so far apart that they'll be invisible to one another, leading to a cold, dark, and isolated cosmos. This scenario, often called the Big Freeze, is just one of several possible outcomes. Other theories suggest that dark energy could evolve over time, potentially leading to a big rip, where the fabric of space itself is torn apart. These dramatic possibilities highlight just how much is still unknown about this enigmatic force. The search for answers has spurred groundbreaking experiments and missions. Projects like the Dark Energy Survey and the upcoming Euclid Space Telescope aim to map the universe in unprecedented detail, hoping to uncover clues about dark energy's nature. These efforts could not only solve the mystery of dark energy, but also reveal new insights into the fundamental laws that govern our universe. In the end, dark energy is more than just a cosmic curiosity. It's a reminder of how much we still have to learn. It challenges our understanding of space, time, and gravity, pushing the boundaries of science in ways that could lead to revolutionary discoveries. As we continue to explore this profound mystery, one thing is clear: the universe is far more complex and wondrous than we ever imagined. And with each new discovery, we take one step closer to unraveling its deepest secrets. Now, shifting our gaze to another cosmic enigma, let's explore the Great Attractor, a mysterious gravitational anomaly that has puzzled astronomers for decades. Imagine a force so powerful that it's pulling entire galaxies, including our own Milky Way, toward it at incredible speeds. This unseen force lies in the direction of the constellations Centaurus and Hydra, about 250 million light-years away. But here's the catch: despite its immense influence, we still don't know what it is or why it exists. The Great Attractor was first discovered in the 1970s when astronomers noticed that galaxies in our local universe were moving in a peculiar way. Instead of spreading out evenly as the universe expands, these galaxies seem to be drawn toward a specific region of space. This movement defied expectations, suggesting the presence of a massive gravitational source. But when scientists tried to observe it directly, they hit a roadblock. The Great Attractor lies in a part of the sky obscured by the dense plane of the Milky Way, making it incredibly difficult to study. What makes this phenomenon even more intriguing is the sheer scale of its influence. The Great Attractor isn't just pulling a few galaxies, it's tugging on thousands, including our own, at speeds of hundreds of kilometers per second. This suggests that whatever lies at its core is unimaginably massive, possibly containing the equivalent of tens of thousands of galaxies. Yet, despite its size, it remains hidden from our view, shrouded in cosmic dust and stars. One theory suggests that the Great Attractor could be a supercluster of galaxies, a dense region where galaxies are packed together more tightly than usual. Superclusters are known to exert strong gravitational pulls, but the Great Attractor's influence seems to extend far beyond what we'd expect from even the largest known superclusters. Another possibility is that it's part of an even larger structure, like the Laniakea supercluster, which encompasses our Milky Way and countless other galaxies. But even within this vast network, the Great Attractor stands out as a gravitational focal point, drawing everything toward it. The mystery deepens when we consider what lies beyond the Great Attractor. Some scientists believe that it might not be the ultimate source of this gravitational pull. Instead, there could be an even more massive structure, nicknamed the Shapley Attractor, located even farther away, exerting its influence on the Great Attractor itself. This idea suggests a cosmic hierarchy of gravitational forces, with each layer pulling on the next, creating a complex web of motion across the universe. Despite the challenges of studying the Great Attractor, advancements in technology are slowly peeling back the veil. Infrared and radio telescopes, which can see through the Milky Way's obscuring dust, have provided glimpses of the galaxies and structures in this region. Projects like the Square Kilometre Array and future space telescopes promise to reveal even more, potentially uncovering the true nature of this cosmic mystery. The Great Attractor reminds us that even in an age of advanced astronomy, the universe still holds secrets that defy our understanding. It challenges us to look beyond what we can see and to question the forces that shape our cosmic neighborhood. As we continue to explore this gravitational anomaly, one thing is certain. The Great Attractor is a testament to the universe's endless capacity to surprise and inspire. And with each new discovery, we come closer to unraveling the mysteries that lie hidden in the depths of space. Now, let's dive deeper into the challenges of mapping the Great Attractor and the ongoing efforts to uncover its secrets. One of the biggest hurdles in studying this gravitational anomaly is its location. The Great Attractor lies in a region of the sky that's heavily obscured by the Milky Way's galactic plane. This dense band of stars, gas, and dust makes it nearly impossible for traditional optical telescopes to peer through and observe what lies beyond. It's like trying to look through a thick fog, only the fog is made of billions of stars and cosmic debris. To overcome this obstacle, scientists have turned to alternative methods of observation. Infrared and radio telescopes have become invaluable tools in this quest. Unlike visible light, infrared and radio waves can penetrate the Milky Way's obscuring dust, allowing astronomers to catch glimpses of the galaxies and structures hidden behind it. These observations have revealed a complex web of galaxies and clusters in the direction of the Great Attractor, hinting at the immense scale of this gravitational force. One of the most significant breakthroughs in mapping the Great Attractor came with the discovery of the Norma cluster, a dense collection of galaxies located near the heart of this mysterious region. The Norma cluster is one of the most massive galaxy clusters in the nearby universe, and its gravitational pull is thought to contribute significantly to the Great Attractor's overall influence. However, even with this discovery, the Great Attractor's true nature remains elusive. The Norma cluster alone doesn't fully account for the immense gravitational force observed, suggesting that there's still much more to uncover. Adding to the complexity is the possibility that the Great Attractor is part of an even larger structure. Astronomers have identified the Laniakea supercluster, a vast network of galaxies that includes our Milky Way and spans over 500 million light-years. Within this supercluster, the Great Attractor acts as a gravitational focal point, drawing galaxies toward it. But even within this colossal structure, the Great Attractor stands out as a unique and puzzling feature. Its influence extends far beyond what we'd expect from a typical supercluster, raising questions about what lies at its core. Ongoing research efforts are focused on unraveling these mysteries. Projects like the Square Kilometre Array, a next-generation radio telescope, promise to provide unprecedented insights into the Great Attractor and its surroundings. By mapping the distribution of galaxies and measuring their movements with incredible precision, scientists hope to piece together a clearer picture of this gravitational anomaly. Additionally, future space telescopes equipped with advanced infrared capabilities could further penetrate the Milky Way's obscuring dust, revealing hidden structures and shedding light on the Great Attractor's true nature. The challenges of studying the Great Attractor highlight the ingenuity and determination of astronomers. Despite the obstacles, each new discovery brings us closer to understanding this cosmic enigma. As we continue to map the Great Attractor and explore its mysteries, we're reminded of the vastness and complexity of the universe and the endless possibilities for discovery that lie ahead. Now, shifting our gaze to another cosmic mystery, let's explore the Fermi Bubbles, two colossal structures of gamma-ray emissions that stretch above and below the Milky Way. Discovered in 2010 by NASA, a Fermi gamma-ray space telescope, these enormous bubbles extend tens of thousands of light-years from the galactic center, dwarfing even the Milky Way itself in scale. Imagine two massive balloons of energy, each towering over our galaxy, emitting intense gamma rays that baffle scientists to this day. The Fermi bubbles are invisible to the naked eye, but their gamma ray emissions reveal their presence. These bubbles are thought to be the remnants of some incredibly energetic event that occurred in the heart of our galaxy, though the exact cause remains a mystery. One leading theory suggests that they were created by a massive outburst from the supermassive black hole at the center of the Milky Way, known as Sagittarius, a star. This black hole, which is millions of times more massive than our Sun, could have unleashed a tremendous burst of energy in the past, sending shock waves and particles racing outward to form these gigantic structures. Another possibility is that the Fermi bubbles are the result of a period of intense star formation near the galactic center. When massive stars are born and die in rapid succession, they can produce powerful stellar winds and supernova explosions, which might have collectively contributed to the formation of these bubbles. However, neither of these theories fully explains the sheer size and energy of the Fermi bubbles, leaving scientists with more questions than answers. What makes the Fermi bubbles even more intriguing is their symmetry. These structures are nearly identical in size and shape, stretching symmetrically above and below the galactic plane. This symmetry suggests a single cataclysmic event as their origin, rather than a series of smaller events. Yet, the exact nature of that event remains one of the most tantalizing mysteries in modern astrophysics. Adding to the intrigue, the Fermi bubbles are not just a relic of the past, they are still active. Observations show that the bubbles are emitting gamma rays even today, indicating that whatever process created them might still be ongoing. This ongoing activity raises the possibility that the Milky Way's central black hole or other energetic processes are still influencing these structures, making them a dynamic and evolving feature of our galaxy. As scientists continue to study the Fermi bubbles, they hope to uncover clues about the history and behavior of our galaxy. Advanced telescopes and simulations are being used to model the formation of these structures, while new observations aim to reveal more about their composition and energy sources. Each discovery brings us closer to understanding these enigmatic giants, but for now, the Fermi bubbles remain a stunning reminder of the mysteries that still surround us in the cosmos. With this in mind, let's turn our attention to the theories that attempt to explain the origins of these colossal structures and why they continue to spark debate among astronomers. Now, as we delve deeper into the Fermi bubbles, let's explore the leading theories that attempt to explain their origins and why these ideas are still hotly debated among scientists. One of the most compelling hypotheses points to the supermassive black hole at the center of our galaxy, Sagittarius, a star. This colossal black hole, with its immense gravitational pull, could have experienced a period of intense activity in the past, releasing an enormous burst of energy. This outburst might have sent jets of particles and radiation shooting out from the galactic center, carving out the massive Fermi bubbles we observe today. The symmetry of the bubbles supports this idea, as it suggests a single, powerful event rather than a series of smaller ones. However, not all researchers are convinced. Some argue that the Fermi bubbles could be the result of galactic winds, streams of charged particles and gas driven by the birth and death of massive stars near the galactic center. When stars form and explode in rapid succession, they can create powerful stellar winds and supernova shocks, which might have collectively shaped these enormous structures. This theory ties the bubbles to the natural life cycle of stars, rather than a singular cataclysmic event. Yet, even this explanation struggles to account for the sheer scale and energy of the Fermi bubbles, leaving room for doubt. Adding another layer to the debate, some scientists propose that the bubbles could be the result of a combination of factors. For instance, the supermassive black hole and intense star formation might have worked together to create these structures. Perhaps a burst of activity from Sagittarius, a star, triggered a chain reaction, amplifying the effects of stellar winds and supernova. This hybrid theory attempts to bridge the gap between the two leading ideas, but it still lacks definitive evidence to fully resolve the mystery. What makes the Fermi bubbles particularly challenging to explain is their ongoing activity. Unlike static remnants of past events, these structures are still emitting gamma rays, suggesting that the processes that formed them might still be at work. This dynamic nature raises questions about whether the bubbles are the result of a one-time event or an ongoing phenomenon tied to the Milky Way's central black hole or other energetic processes. It's this combination of scale, symmetry, and activity that keeps the debate alive and fuels the curiosity of astronomers. As researchers continue to study the Fermi bubbles, they're using advanced telescopes and computer simulations to test these theories. Each new observation brings us closer to understanding these enigmatic structures, but for now, they remain one of the most fascinating unsolved puzzles in our galaxy. With so many questions still unanswered, the Fermi bubbles remind us that even in our own cosmic backyard, there are mysteries waiting to be unraveled. And as we move forward, let's turn our attention to another cosmic enigma, the WOW signal, a mysterious radio signal that has puzzled scientists for decades. Shifting our gaze from the enigmatic Fermi bubbles, we now turn to one of the most intriguing mysteries in the search for extraterrestrial intelligence, the WOW signal. Detected on August 15, 1977, this powerful radio signal has captivated scientists and enthusiasts alike for decades. It was picked up by the Big Ear radio telescope at Ohio State University, and its unusual characteristics immediately stood out. The signal lasted for 72 seconds and was so strong that astronomer Jerry Amon, who discovered it, circled the data on the printout and wrote, "Wow." Next to it, a name that has stuck ever since. What made the WOW signal so remarkable was its frequency. It appeared at around 1,420 MHz, a range that falls within the water hole, a band of frequencies considered ideal for interstellar communication. This frequency is significant because it's relatively quiet, with minimal interference from natural cosmic sources, making it a logical choice for any civilization attempting to send a message across the stars. The signal's intensity also suggested it originated from a powerful source, possibly far beyond our solar system. Yet, despite its strength and specificity, the signal was never detected again, leaving scientists puzzled. The mystery deepens when we consider the signal's origin. It appeared to come from the direction of the constellation Sagittarius, near the star group Chi Sagittarii, but no known celestial object in that region could explain such a strong, narrowband signal. This has led to widespread speculation about its source. Could it have been a message from an advanced extraterrestrial civilization? Or was it a natural phenomenon that we simply don't yet understand? The lack of a repeat signal makes it difficult to draw any definitive conclusions, and the WOW signal remains one of the most tantalizing unsolved mysteries in astronomy. Adding to the intrigue, the WOW signal's brevity and uniqueness have made it a focal point in the search for extraterrestrial intelligence, or SETI. Over the years, numerous attempts have been made to detect a similar signal from the same region of space, but none have succeeded. This has led some to propose that the signal might have been a one-time event, such as a burst of energy from a distant star or even a passing spacecraft reflecting signals back to Earth. However, none of these explanations fully account for the signal's characteristics, leaving the door open to the possibility of an extraterrestrial origin. The WOW signal continues to inspire curiosity and debate, reminding us of the vast unknowns that still exist in our universe. As we explore the cosmos, signals like this challenge our understanding and fuel our imagination, pushing us to ask profound questions about our place in the universe. And as we ponder the mysteries of the WOW signal, let's move on to another cosmic puzzle, Tabby's star, a celestial object whose strange dimming patterns have sparked theories ranging from dust clouds to alien megastructures. The WOW signal has become a cornerstone in the search for extraterrestrial life, sparking both excitement and skepticism in equal measure. Its brief yet powerful nature has led scientists to wonder if it could be a glimpse of intelligent life beyond Earth. While the signal itself remains unexplained, its implications have fueled decades of research and technological advancements in the field of SETI, or the search for extraterrestrial intelligence. One of the most significant outcomes of the WOW signal has been the push to develop more sophisticated tools and methods to detect potential alien communications. Modern radio telescopes like the Allen Telescope Array and the upcoming Square Kilometre Array are designed to scan vast regions of the sky with unprecedented sensitivity. These instruments aim to pick up signals that might be too faint or fleeting for older technology to detect, increasing the chances of finding something as extraordinary as the WOW signal again. But the search isn't just about technology, it's also about strategy. Scientists have refined their approach by focusing on specific frequencies like the waterhole, where the WOW signal was detected. This range between 1,420 and 1,660 MHz is considered a sweet spot for interstellar communication because it's relatively free from cosmic noise. By concentrating their efforts here, researchers hope to maximize the likelihood of discovering a signal that could be intentional. Another intriguing aspect of the search is the growing interest in technosignature's evidence of advanced technology, such as megastructures or artificial signals that could indicate the presence of intelligent life. While the WOW signal remains a mystery, it has inspired scientists to broaden their scope beyond traditional radio signals. For example, some researchers are now looking for laser pulses or other forms of communication that might be used by civilizations far more advanced than our own. Despite these efforts, the WOW signal stands alone as a unique and unexplained event. Its singularity has led some to question whether it was truly a message from another civilization or simply a rare natural phenomenon that we don't yet understand. This uncertainty keeps the search alive, driving scientists to explore every possible explanation while remaining open to the extraordinary possibility that we are not alone in the universe. As we continue to scan the skies for signs of life, the WOW signal serves as a powerful reminder of the mysteries that still await us. It challenges us to think beyond our current understanding and to remain curious about the vast, uncharted reaches of space. And with that, let's turn our attention to another cosmic enigma, Tabby star, whose unusual dimming patterns have sparked theories ranging from dust clouds to alien megastructures. Now, let's shift our gaze to a star that has captured the imagination of astronomers and science enthusiasts alike. Tabby star, officially known as KIC 8462852, this star gained fame for its bizarre and unpredictable dimming patterns, which have sparked a whirlwind of theories, including the tantalizing possibility of alien megastructures. Located roughly 1,400 light-years away in the constellation Cygnus, Tabby star was first observed by NASA Kepler Space Telescope. What makes this star so unusual is the way its brightness fluctuates. Unlike most stars, which dim in predictable, periodic ways due to orbiting planets or natural stellar activity, Tabby star experiences irregular and dramatic dips in brightness, sometimes by as much as 22%. These dips can last for days or even weeks, and they don't follow any clear pattern, leaving scientists scratching their heads. One of the most intriguing explanations for these strange dimming patterns is the idea of alien megastructures. Some researchers have suggested that the dips in brightness could be caused by a massive artificial object, like a Dyson sphere, orbiting the star. A Dyson sphere is a hypothetical structure that an advanced civilization might build to harness the energy of a star. If such a structure were partially completed or unevenly constructed, it could block varying amounts of light as it moves, creating the irregular dimming patterns we observe. However, before we jump to conclusions about extraterrestrial engineering, it's important to consider natural explanations as well. One leading theory is that the dimming could be caused by vast clouds of dust or debris orbiting the star. These clouds could be the remnants of a shattered planet or comet, or even a swarm of smaller objects like asteroids. Dust clouds can scatter and absorb light in unpredictable ways, which might account for the star's erratic behavior. Another possibility is that Tabby's star is surrounded by a massive ring system, far larger and more complex than Saturn's. Such a ring system, tilted at just the right angle, could periodically block the star's light as it rotates. While this would be an extraordinary discovery in itself, it still falls within the realm of natural phenomena. Despite these plausible explanations, the mystery of Tabby's star remains unsolved. Its unusual behavior has inspired countless studies, with astronomers using advanced telescopes and instruments to gather more data. Each new observation brings us closer to understanding what's really happening around this enigmatic star, but for now, it continues to defy easy explanation. Tabby's star serves as a fascinating reminder of how much we still have to learn about the universe. Whether its dimming patterns are caused by alien megastructures, cosmic dust, or something entirely unexpected, this star challenges us to think creatively and remain open to the extraordinary possibilities that lie beyond our current understanding. And with that, let's move on to another cosmic mystery, the Oort Cloud, a vast and elusive region at the edge of our solar system that holds secrets of its own. Now, let's take a closer look at the natural explanations that might shed light on the strange behavior of Tabby's star. While the idea of alien megastructures is undeniably exciting, scientists have been hard at work exploring more grounded possibilities that could explain the star's erratic dimming patterns. One of the leading theories involves vast clouds of dust or debris orbiting the star. These clouds could be the remnants of a shattered planet, a disintegrating comet, or even a swarm of smaller objects like asteroids. Dust clouds are known to scatter and absorb light in unpredictable ways, which could account for the irregular dips in brightness we observe. Another compelling theory suggests that Tabby's star might be surrounded by a massive and complex ring system, far larger than anything we've seen in our own solar system. Imagine a ring system so vast and tilted at just the right angle that it periodically blocks the star's light as it rotates. While this would be an extraordinary discovery, it's still a natural phenomenon, albeit one that pushes the boundaries of what we know about stellar environments. Some researchers have also proposed that the star's unusual behavior could be linked to its own internal processes. For instance, Tabby's star might be undergoing significant stellar activity, such as massive sunspots or magnetic storms, which could cause temporary and irregular dimming. While this explanation doesn't require any external factors, it still leaves room for further investigation, as the scale and frequency of such activity would need to be unprecedented to match the observations. Despite these plausible natural explanations, the mystery of Tabby's star persists. Each theory has its own set of challenges and unanswered questions. For example, if dust clouds are responsible, why don't they produce the infrared signatures we'd expect to see? And if it's a ring system, how did it form and why is it so massive? These lingering questions keep astronomers intrigued and motivated to gather more data. The ongoing study of Tabby's star is a testament to the scientific process, observing, hypothesizing, and refining our understanding as new evidence emerges. While we may not have all the answers yet, the star continues to challenge our assumptions and inspire us to think beyond the ordinary. Whether the solution lies in cosmic dust, colossal rings, or something entirely unexpected, Tabby's star reminds us that the universe is full of surprises waiting to be uncovered. And with that, let's turn our attention to the next cosmic enigma, the Oort Cloud, a distant and mysterious region that holds clues to the origins of our solar system. Now, let's venture beyond the familiar boundaries of our solar system to explore one of its most elusive mysteries, the Oort Cloud. Imagine a vast spherical shell of icy objects, stretching far beyond the orbit of Pluto, at the very edge of the Sun's gravitational influence. This is the Oort Cloud, a theoretical region that scientists believe is home to trillions of icy bodies, some of which may have been drifting there since the formation of the solar system over 4.5 billion years ago. The Oort Cloud is thought to be the source of long-period comets, those rare visitors that occasionally streak through our skies after traveling unimaginable distances. These comets, with their long, looping orbits, are believed to originate from this distant reservoir, nudged out of their icy slumber by the gravitational pull of passing stars or even the Milky Way itself. Yet, despite its significance, the Oort Cloud has never been directly observed. Why is that? The answer lies in its sheer distance. The Oort Cloud is estimated to begin around 2,000 times farther from the Sun than Earth, and it extends even farther into the depths of space. At such immense distances, the objects within the Oort Cloud are incredibly faint, making them nearly impossible to detect with current technology. Even the most powerful telescopes struggle to pick up the faint glimmer of these icy bodies against the vast backdrop of space. Adding to the challenge is the fact that the Oort Cloud is not a dense, tightly packed region. Instead, it's a sparse and diffuse collection of objects spread out over an enormous volume. This means that even if we could observe it directly, the individual objects would be so far apart that detecting them would be like finding a single grain of sand in a desert. Despite these obstacles, scientists are confident the Oort Cloud exists because of the behavior of long-period comets. Their trajectories suggest they come from a distant spherical shell, aligning perfectly with the theoretical model of the Oort Cloud. Additionally, the cloud's existence helps explain how the solar system retains its outermost icy material, acting as a cosmic freezer preserving remnants from its earliest days. The Oort Cloud remains one of the most tantalizing mysteries in our solar system, a place where the past is frozen in time, waiting to be uncovered. While we may not have the technology to observe it directly just yet, its presence reminds us that there's still so much to discover about the far reaches of our cosmic neighborhood. And as we continue to push the boundaries of exploration, who knows what secrets the Oort Cloud might reveal? Next, we'll dive into the challenges of studying this distant region and the ongoing efforts to unlock its mysteries. Now, let's take a closer look at how scientists are piecing together the puzzle of the Oort Cloud, even though it remains hidden from direct observation. One of the key ways researchers infer its existence is by studying the paths of long-period comets. These comets, with their highly elliptical orbits, seem to originate from a distant spherical region far beyond the planets. By tracing their trajectories backward, scientists can map out where these icy travelers likely began their journey, pointing to the Oort Cloud as their source. Another clue comes from the way these comets behave. Unlike short-period comets, which are influenced by the gravity of planets like Jupiter, long-period comets appear to come from all directions, suggesting a spherical shell rather than a flat, disk-like structure. This aligns perfectly with the theoretical model of the Oort Cloud, reinforcing the idea that it's a vast, three-dimensional reservoir of icy bodies. But studying the Oort Cloud isn't just about observing comets. Scientists also rely on computer simulations to model how such a distant region could have formed and evolved over billions of years. These simulations suggest that the Oort Cloud is a remnant of the early solar system, a place where leftover material from the formation of planets was flung outward by the gravitational influence of giant planets like Jupiter and Saturn. Over time, this material settled into a distant, icy shell, preserved in the cold depths of space. Despite these insights, the challenges of studying the Oort Cloud are immense. Its extreme distance means that even the most advanced telescopes struggle to detect its faint, icy objects. The Hubble Space Telescope, for example, has peered into the depths of space for decades, but the Oort Cloud remains just out of reach. Adding to the difficulty is the fact that the objects within the cloud are spread out over an enormous volume, making them incredibly sparse and hard to spot. To overcome these challenges, scientists are turning to innovative techniques. One approach involves searching for the faint glow of sunlight reflecting off the icy surfaces of Oort Cloud objects. While this method has yet to yield direct observations, it holds promise for future breakthroughs. Another strategy is to study the gravitational effects of the Oort Cloud on nearby stars or passing objects, looking for subtle clues that could reveal its presence. As we continue to push the boundaries of technology and exploration, the Oort Cloud remains a tantalizing target for discovery. It's a reminder that even in our own cosmic backyard, there are still mysteries waiting to be uncovered. And while we may not have all the answers yet, the search for the Oort Cloud is a testament to humanity's enduring curiosity and determination to understand the universe. Next, we'll explore another enigmatic phenomenon that challenges our understanding of space, the Pioneer Anomaly, an unexpected twist in the journey of one of humanity's most iconic spacecraft. Now, shifting our gaze from the distant Oort Cloud to the journeys of humanity's own spacecraft, we encounter another perplexing mystery, the Pioneer Anomaly. In the late 1970s, as the Pioneer 10 and Pioneer 11 spacecraft ventured beyond the outer planets, scientists noticed something strange. Both probes were slowing down slightly more than expected, a tiny but consistent deviation from their predicted trajectories. This unexpected deceleration, though small, became a source of fascination and frustration for researchers, sparking decades of investigation. At first, the anomaly seemed almost negligible. The spacecraft was slowing down by about 300 millionths of a meter per second squared, a minuscule amount, but one that couldn't be ignored. Over time, this tiny discrepancy added up, causing the probes to drift off course by hundreds of kilometers. Scientists scrambled to find an explanation, considering everything from errors in their calculations to the influence of unknown forces in space. One of the most intriguing possibilities was that the anomaly might hint at new physics, perhaps even a flaw in our understanding of gravity. Could there be some unseen force at work, bending the rules of the universe as we know them? For years, this idea captivated the scientific community, with theories ranging from the influence of dark matter to the existence of extra dimensions. The Pioneer Anomaly became a symbol of the unknown, a reminder that even our most advanced technology could still be humbled by the mysteries of the cosmos. However, after decades of scrutiny, the most likely explanation turned out to be far more mundane, yet no less fascinating. Researchers eventually concluded that the anomaly was caused by thermal radiation, heat emitted unevenly from the spacecraft's power systems. As the probe's radioactive power sources decayed, they released heat that pushed against the spacecraft in subtle, asymmetrical ways, creating the observed deceleration. While this explanation solved the puzzle, it also highlighted the incredible precision required to navigate the vastness of space. The Pioneer Anomaly serves as a testament to the challenges of space exploration and the importance of questioning even the smallest discrepancies. It reminds us that sometimes the answers to the universe's mysteries lie not in grand cosmic forces, but in the intricate details of our own technology. As we continue to explore the cosmos, anomalies like this one push us to refine our tools, sharpen our understanding, and remain ever curious about the unknown. Next, we'll delve into another cosmic puzzle, the Kuiper Belt's missing mass, and why this region of our solar system continues to defy expectations. Now, as we dig deeper into the Pioneer Anomaly, let's explore how this cosmic puzzle was finally unraveled. After years of meticulous analysis, scientists pinpointed the culprit behind the spacecraft's unexpected deceleration, thermal radiation. The Pioneer probes were powered by radioactive isotopes which generated heat as they decayed over time. This heat wasn't distributed evenly across the spacecraft. Instead, it radiated more strongly from certain areas, creating a subtle but consistent push against the probes. This uneven thermal radiation acted like an invisible hand, gently slowing the spacecraft down in a way that initially baffled researchers. What makes this discovery so fascinating is how it underscores the complexity of space exploration. Even the tiniest details, like the way heat escapes from a spacecraft, can have profound effects on its trajectory. the Pioneer Anomaly reminds us that space is a realm of precision, where even the smallest forces can lead to big mysteries. While the explanation may seem straightforward now, it took decades of collaboration, innovation, and sheer determination to uncover the truth. This journey highlights the importance of questioning every anomaly, no matter how insignificant it may seem at first. Yet, even with this explanation, the Pioneer Anomaly remains a captivating chapter in the story of space exploration. It serves as a reminder that our understanding of the cosmos is always evolving. What we once thought might be evidence of new physics turned out to be a lesson in the intricate interplay of technology and the environment of space. This anomaly also paved the way for future missions, encouraging engineers to design spacecraft with even greater precision and to account for every possible variable, no matter how small. So, while the mystery of the Pioneer Anomaly has been solved, its legacy endures. It's a testament to the relentless curiosity of scientists and the endless surprises that await us in the vastness of space. As we move forward, let's turn our attention to another cosmic enigma, the Kuiper Belt's missing mass, a puzzle that continues to challenge our understanding of the solar system's outer reaches. Now, shifting our gaze to the outer edges of our solar system, we encounter another cosmic mystery, the Kuiper Belt's missing mass. The Kuiper Belt, a vast region beyond Neptune filled with icy bodies, comets, and dwarf planets like Pluto, has long fascinated astronomers. But here's the puzzle: when scientists calculated the total mass of all the objects in this belt, they found it to be far less than what they expected. Based on models of how the solar system formed, the Kuiper Belt should contain significantly more material than what we've observed. This discrepancy has left researchers scratching their heads, wondering where all the missing mass could have gone. One theory suggests that much of the Kuiper Belt's original mass might have been ejected into interstellar space during the early days of the solar system. As the giant planets like Jupiter and Saturn migrated outward, their immense gravitational pull could have flung countless icy objects out of the Kuiper Belt, scattering them far beyond our reach. Another possibility is that the missing mass is still there, but in forms we can't easily detect. Perhaps it's hidden in smaller, darker objects that are too faint for our telescopes to spot, or maybe it's locked away in larger bodies that have yet to be discovered. What makes this mystery even more intriguing is its connection to the formation of the solar system. The Kuiper Belt is like a time capsule, preserving clues about the conditions and processes that shaped our cosmic neighborhood billions of years ago. If we can solve the riddle of its missing mass, we might gain new insights into how planets form and evolve, not just in our own solar system but across the universe. For now, though, the Kuiper Belt keeps its secrets, challenging us to look deeper and think harder about the forces that govern the cosmos. As we ponder this enigma, let's turn our attention to another fascinating phenomenon: the Moon's mysterious magnetic field, a puzzle that has puzzled scientists for decades and continues to spark new theories and discoveries. Now let's delve deeper into the theories surrounding the Kuiper Belt's missing mass, a puzzle that continues to challenge our understanding of the solar system. One compelling hypothesis suggests that the missing mass might be hiding in plain sight, just in forms we haven't yet detected. For instance, there could be countless smaller, darker objects scattered throughout the Kuiper Belt, objects so faint and distant that even our most advanced telescopes struggle to spot them. These elusive bodies, if they exist, could account for the discrepancy in mass, quietly orbiting the Sun without revealing themselves to our instruments. Another intriguing possibility is that the missing mass was lost long ago, during the chaotic early days of the solar system. Imagine a time when the giant planets were still settling into their orbits, their immense gravitational forces reshaping the cosmic landscape. As Jupiter and Saturn migrated outward, their gravitational pull could have flung vast numbers of icy objects out of the Kuiper Belt, sending them hurtling into interstellar space. This dramatic scattering of material might explain why the belt appears lighter than expected, with much of its original mass now lost to the void. But what if the missing mass isn't lost at all? Some scientists propose that it could be concentrated in larger, yet-to-be-discovered bodies. These hypothetical objects, perhaps even dwarf planets or massive comets, might be lurking in the outer reaches of the Kuiper belt, evading detection due to their distance or faintness. If such bodies exist, they could hold the key to solving this cosmic mystery, offering a glimpse into the solar system's formative years. What makes this mystery so enduring is its connection to the broader story of our solar system's evolution. The Kuiper belt isn't just a collection of icy debris. It's a window into the past, preserving clues about the forces that shaped our cosmic neighborhood. Solving the riddle of its missing mass could unlock new insights into how planets form, how materials are distributed in space, and even how other star systems might evolve. For now, though, the Kuiper belt keeps its secrets, reminding us that even in our own cosmic backyard, there's still so much to discover. As we continue our journey through the mysteries of space, let's turn our attention to another celestial enigma: the Moon's magnetic field, a phenomenon that has puzzled scientists for decades and continues to inspire new questions about our closest cosmic neighbor. Now, shifting our gaze closer to home, let's explore one of the Moon's most intriguing mysteries: its magnetic field. Unlike Earth, which has a strong, active magnetic field generated by its molten core, the Moon today is essentially magnetically silent. But here's the twist: billions of years ago, the Moon had a magnetic field, and a surprisingly strong one at that. Evidence from lunar rocks brought back by the Apollo missions shows that the Moon once had a magnetic field about 100 times stronger than it does today. This discovery has left scientists scratching their heads, wondering how a relatively small body like the Moon could have generated such a powerful magnetic field in the first place, and why it vanished. One leading theory suggests that the Moon's magnetic field was powered by a molten core, much like Earth's. In its early days, the Moon's interior was hot and dynamic, with a liquid core that could generate a magnetic field through a process called dynamo action. This process involves the movement of molten metal within the core, creating electric currents that produce a magnetic field. But as the Moon cooled over time, its core likely solidified, shutting down the dynamo and causing the magnetic field to fade away. This explanation seems straightforward, but it raises another question. Why did the Moon's core cool so much faster than Earth's, leading to the disappearance of its magnetic field? Another fascinating possibility is that the Moon's magnetic field wasn't generated by its core alone, but was influenced by external forces. Some scientists propose that the Moon's magnetic field might have been amplified by its proximity to Earth during its early history. As the Moon orbited closer to Earth, tidal forces could have stirred its interior, keeping the core molten and active for longer than expected. Over time, as the Moon drifted further away, these tidal forces weakened, allowing the core to cool and the magnetic field to dissipate. This theory adds an intriguing layer to the story, suggesting that the Moon's magnetic history is deeply intertwined with its relationship to Earth. Yet, despite these theories, the mystery of the Moon's magnetic field remains unsolved. The lunar rocks that hold the key to this puzzle are billions of years old, and interpreting their magnetic signatures is no easy task. Scientists continue to study these ancient relics, searching for clues that could explain how the Moon's magnetic field worked and why it disappeared. This mystery isn't just about the Moon. It's about understanding how magnetic fields form and evolve in planetary bodies, offering insights that could apply to other moons and planets in our solar system and beyond. As we ponder the Moon's magnetic past, we're reminded that even our closest cosmic neighbor holds secrets waiting to be uncovered. Next, we'll turn our attention to another mind-bending mystery: the black hole information paradox, a puzzle that challenges the very foundations of physics. Now let's dive deeper into the theories surrounding the moon's magnetic field and why this cosmic puzzle continues to baffle scientists. One of the most widely accepted explanations revolves around the idea of a molten core. Just like Earth, the moon may have once had a hot, liquid core that generated a magnetic field through a process known as dynamo action. This process involves the movement of molten metal within the core, creating electric currents that produce a magnetic field. However, as the moon's interior cooled over billions of years, its core likely solidified, shutting down the dynamo and causing the magnetic field to fade. But here's the catch: the moon is much smaller than Earth, so why did its core cool so much faster? This question remains unanswered, leaving scientists to wonder if there's more to the story. Another intriguing theory suggests that external forces played a significant role in shaping the moon's magnetic history. During its early days, the moon was much closer to Earth, and the gravitational pull between the two bodies could have created tidal forces strong enough to stir the moon's interior. This stirring might have kept the core molten and active for longer than expected, sustaining the magnetic field. Over time, as the moon drifted further away from Earth, these tidal forces weakened, allowing the core to cool and the magnetic field to disappear. This theory adds a fascinating layer to the mystery, suggesting that the moon's magnetic field wasn't just a product of its own internal dynamics, but also a result of its relationship with Earth. Despite these compelling theories, the mystery of the moon's magnetic field persists. One of the biggest challenges lies in the evidence itself: the lunar rocks brought back by the Apollo missions. These rocks are billions of years old, and interpreting their magnetic signatures is incredibly complex. Scientists are still working to decode the clues hidden within these ancient samples, hoping to uncover the true story behind the moon's magnetic past. What makes this mystery even more intriguing is its broader implications. Understanding how and why the moon's magnetic field disappeared could provide valuable insights into the magnetic histories of other planetary bodies, both in our solar system and beyond. As we continue to explore this cosmic enigma, one thing is clear: the moon's magnetic field is a reminder of how much we still have to learn about the universe. Even our closest celestial neighbor holds secrets that challenge our understanding of planetary science. And with that, we'll now turn our attention to another mind-bending mystery: the black hole information paradox, a puzzle that pushes the boundaries of physics itself. Now, let's venture into one of the most perplexing mysteries in modern physics: the black hole information paradox. At its core, this paradox challenges one of the fundamental principles of quantum mechanics, the idea that information cannot be destroyed. In the quantum world, every particle, every interaction, leaves behind a kind of footprint that can, in theory, be traced back. But when it comes to black holes, this rule seems to break down. Here's the problem: when matter falls into a black hole, it's thought to be lost forever, crushed into the singularity at the center. But what happens to the information that matter carried? According to quantum mechanics, that information should still exist somewhere, somehow. Yet, black holes appear to erase it completely, creating a direct contradiction between the laws of quantum physics and our understanding of black holes. This paradox has puzzled scientists for decades, forcing them to rethink some of the most basic assumptions about how the universe works. The implications of this paradox are enormous. If information truly disappears in a black hole, it would mean that our current understanding of physics is incomplete. It would require a radical shift in how we think about space, time, and the very nature of reality. On the other hand, if information isn't lost, where does it go? This question has sparked some of the most fascinating and groundbreaking theories in modern science, including the idea of Hawking radiation, which we'll explore next. As we peel back the layers of this cosmic mystery, one thing becomes clear: the black hole information paradox isn't just a theoretical puzzle, it's a gateway to deeper questions about the universe itself. And with that, we'll now turn to the next piece of this cosmic puzzle: Hawking radiation and its role in this ongoing debate. Now, let's take a closer look at one of the most intriguing ideas to emerge from this cosmic conundrum, Hawking radiation. Proposed by the legendary physicist Stephen Hawking in the 1970s, this theory suggests that black holes aren't entirely black after all. Instead, they emit a faint glow of radiation over time, slowly losing energy and eventually mass. This radiation is thought to arise from quantum effects near the event horizon, the boundary beyond which nothing can escape a black hole's gravitational pull. Here's how it works. According to quantum mechanics, empty space isn't truly empty. It's filled with pairs of particles and antiparticles that constantly pop into existence and annihilate each other. Near a black hole's event horizon, one of these particles can fall into the black hole while the other escapes into space. The escaping particle carries away energy, which over time causes the black hole to shrink. This process is what we call Hawking radiation, but here's where things get even more fascinating and puzzling. If Hawking radiation is real, it implies that black holes aren't eternal. They evaporate, leaving behind only the radiation they've emitted. But what happens to the information that fell into the black hole? If it's encoded in the radiation, as some theories suggest, then the information paradox might be resolved. However, this raises new questions. How exactly is the information preserved, and can it ever be retrieved? Despite decades of research, scientists still don't have a definitive answer. Some argue that the information is scrambled and lost forever, while others believe it's somehow encoded in the radiation in a way we don't yet understand. This ongoing debate has led to groundbreaking ideas such as the holographic principle, which suggests that all the information about what falls into a black hole could be stored on its surface like a cosmic hologram. The mystery of Hawking radiation and the black hole information paradox continues to challenge our understanding of the universe. It's a reminder that even the most brilliant minds like Stephen Hawking could only scratch the surface of these profound questions. And as we move forward, we'll explore another cosmic mystery that pushes the boundaries of our knowledge, the Eridanus supervoid, a vast and puzzling emptiness in the fabric of space. Now, shifting our gaze to another cosmic enigma, we encounter the Eridanus supervoid, a colossal emptiness in the universe that defies our expectations. Imagine a region of space so vast and empty that it stretches across nearly 1 billion light-years, a staggering expanse where galaxies are few and far between. This supervoid, located in the constellation Eridanus, is one of the largest structures ever discovered. Yet its existence challenges the very foundations of our understanding of the cosmos. According to the standard cosmological model, the universe should be relatively uniform on large scales, with matter distributed evenly across space. But the Eridanus supervoid disrupts this idea. Its sheer size and emptiness are difficult to reconcile with the predictions of the Big Bang theory and the cosmic microwave background radiation, the afterglow of the early universe. Scientists have observed that this region appears to be colder than its surroundings, a phenomenon known as the cold spot, which adds another layer of mystery to this already puzzling void. One leading theory suggests that the Eridanus supervoid might be the result of a rare cosmic fluctuation, a region where matter simply didn't clump together as expected during the universe's formation. Another intriguing possibility is that the void could be interacting with dark energy in ways we don't yet understand, causing the observed temperature anomalies. Some even speculate that it might be evidence of a collision with another universe, though this idea remains highly speculative. What makes the Eridanus supervoid so fascinating is not just its size, but the questions it raises about the nature of our universe. If such a massive void can exist, what does it mean for our understanding of cosmic structure and evolution? Could there be other voids like it, or is this a unique anomaly? These questions continue to drive research as scientists use advanced telescopes and simulations to probe the secrets of this cosmic emptiness. As we ponder the mysteries of the Eridanus supervoid, we're reminded once again that the universe is full of surprises, challenging us to rethink what we know and inspiring us to explore further. And with that, we turn our attention to another cosmic puzzle that pushes the boundaries of our knowledge even further. Now, as we delve deeper into the enigma of the Eridanus supervoid, let's explore the theories that attempt to explain its formation and why it remains one of the most perplexing mysteries in cosmology. One of the most widely discussed ideas is that the supervoid could be the result of an extremely rare cosmic fluctuation. During the early stages of the universe, matter and energy were not distributed perfectly evenly. In most regions, matter clumped together to form galaxies and clusters, but in the case of the Eridanus supervoid, it's possible that this region simply didn't accumulate enough matter, leaving it unusually empty. This theory aligns with the idea that the universe, on the largest scales, should have some degree of randomness, but the sheer size of the void pushes the limits of what we consider statistically probable. Another compelling theory involves dark energy, the mysterious force driving the accelerated expansion of the universe. Some scientists propose that the Eridanus supervoid might be interacting with dark energy in ways we don't yet fully understand. This interaction could potentially explain the observed temperature anomalies, such as the cold spot, by altering the way light and energy travel through this vast emptiness. If true, this would not only shed light on the void itself, but also provide new insights into the nature of dark energy, one of the greatest unsolved puzzles in modern physics. There's also a more speculative idea that the Eridanus supervoid could be evidence of a collision with another universe. In the multiverse theory, our universe is just one of many, and interactions between these universes could leave behind observable imprints. While this idea is fascinating, it remains highly theoretical and lacks direct evidence. Still, it highlights how the supervoid challenges us to think beyond conventional models and consider possibilities that were once thought to be purely science fiction. What makes the Eridanus supervoid so intriguing is not just its size or emptiness, but the questions it raises about the fundamental nature of the cosmos. If such a massive void can exist, what does it mean for our understanding of the universe's structure and evolution? Are there other voids like it, or is this a unique anomaly? These questions continue to drive research as scientists use advanced telescopes and simulations to probe the secrets of this cosmic emptiness. Each new discovery brings us closer to understanding, but for now, the Eridanus supervoid remains a profound mystery, reminding us that the universe is far more complex and unpredictable than we ever imagined. With this cosmic puzzle still lingering in our minds, let's turn our attention to another phenomenon that pushes the boundaries of our knowledge even further. As we reach the end of our journey through these 25 unexplained space phenomena, one thing becomes abundantly clear: the universe is a place of endless wonder and mystery. From the explosive power of gamma-ray bursts to the eerie emptiness of the Eridanus supervoid, each phenomenon challenges our understanding of the cosmos and reminds us how much we have yet to discover. These mysteries are not just scientific puzzles, they are invitations to explore, to question, and to imagine the possibilities that lie beyond our current knowledge. What makes these phenomena so captivating is not just their complexity, but the way they push the boundaries of what we think we know. Whether it's the strange dimming of Tabby's star, the enigmatic signals from deep space, or the invisible forces of dark matter and dark energy, each mystery offers a glimpse into the vast, uncharted territories of the universe. And while scientists continue to unravel these cosmic secrets, the truth is that some questions may remain unanswered for generations to come, but that's the beauty of it. The universe is not just a collection of facts and figures, it's a story that's still being written, and you, as part of this incredible journey, have the chance to be part of that story. What do you think about these unexplained phenomena? Do you have your own theories or ideas about what might be causing them? Share your thoughts in the comments below. I'd love to hear your perspectives and spark a conversation about the mysteries that captivate us all. If you're as fascinated by the cosmos as I am, don't forget to hit the like button, subscribe to the channel, and ring the notification bell so you never miss an exploration into the wonders of space. There's so much more to uncover, and I can't wait to dive into the next cosmic mystery with you. Until then, keep looking up because the universe is full of surprises, and who knows what we'll discover.